could not make it tonight, the recording will be on UlearnX. They can also access it on MS Teams, and also happy to take questions lah. All right. Welcome everybody. First of all, I'd like to apologize for the delay actually in having our first session. Sorry, I actually meant to do it last week, but had a family member who was admitted to hospital, and last minute I had to take some days leave lah. It was out of state, so I apologize for that. But anyway, I hope you've been able to check out the material on UlearnX. So this semester I'll be teaching you advanced digital systems design, and we have a relatively short semester for those who just joined us, Shazwi and Gabriel. So about 12 weeks. So we're roughly in the third week. So not so many weeks left. And this course, compared to the previous semester's course, is a bit less structured. What I mean by that is because there's really only one really important thing that I would like you to pick up lah. That is the ability to design digital circuits lah. And unlike your undergraduate lah, where you probably learn digital electronics, and when people talk about digital circuits, what comes to mind is state transition diagram. I have this recipe, right? So you remember a recipe, you have your K-maps, you draw some circles, you write some Boolean logic, and then out pops up magically the logic gates lah. So the focus on your undergraduate digital electronics is basically to show you how to apply some kind of mathematical approach or recipe, just to basically figure out how to calculate or how to compute or implement logic as basic logic gates. All right, that's the focus of your undergraduate. But I think I don't know how many of you have tried to design digital circuits since then, and probably you would have seen that it's not so easy to do that, especially when things kind of really scale up, right? And so the focus of this course actually to kind of give you that insight and ability to design complex digital circuits. So that's why it's advanced digital systems design. And one of the tools you'll be using is a software programming language called Verilog. The equivalent is VHDL, right? And these are basically a software way of writing or describing circuits. Okay, and I'd like to just draw your attention to this book, FPGA Prototyping for Systems Verilog Example. This is really an excellent book. If you just click on it, it really will walk you through all the steps and all the code and all the ideas, and you really should be focusing on chapter 4, 5, 6. That's about it. Chapter 1 and 3 is kind of a review of your digital electronics, right? So if you're kind of rusty on that, make sure you really spend the time to review chapter 1 and 3 for your digital electronics. But really the core is actually chapter 4, 5, and 6, and this is under part 1 here. So chapter 1 and 3, this is combinational circuits, very straightforward. But the real meat for digital systems actually comes when you start designing the sequential circuits, and this is the idea of the flip-flop. Okay, and then you have the finite state machines, right, which is basically a sequential circuit, but you learn how to compute the outputs in response to some input and some state, and then what we call the finite state machine for data path. All right, so just kind of just walking you through that. Chapter 4, 5, and 6 really, as soon as you can, within the next 2 to 3 weeks, you really should master this material. And chapter 1 and 3 is something that is very straightforward. You should know this already, but it's just kind of picking up the code, the Verilog code. And why I say it's a great book is because you've got tons of examples here. You've got example of how to design a UART, Universal Asynchronous Receiver Transmitter core. You've got examples how to actually design different things like pulse width modulation, debouncing. How do you design a chip to do SPI communication, to do I2C communication. PS2 is for mouse. Sound one, this is direct digital frequency synthesis. How do you generate sound waves? So you've got tons and tons of examples to refer to how you actually design complex systems. But I said the requirement for this course is 1 and 3 are review. Chapter 4, 5, 6, you must learn this as soon as you can. I would say roughly within the next 3 weeks, right? It was already given here for some time, roughly in the next 3 weeks. So this is the core where you really pick up the basics before we jump into the details lah, the actual hands-on and all that lah. Okay. And this is the second book that I'm giving. But before we talk about that, I also give you this kind of preprint lah. William Daly was formerly a professor at MIT and Stanford University, and also chief scientist at NVIDIA lah. He spent a big part of his life designing supercomputers. I like this book because this is one of the rare digital electronics books where the focus is on systems design. He doesn't spend, he has the chapters again talking about how to do digital electronics, how to do like the K-maps and all that, but he doesn't spend most of the chapters there. Most of the chapters are actually real system examples, how he designs various types of circuits, and they are example problems. So it's a great reference. This one actually is not an official copy, it's an early version. I managed to find it on the web and I just share with you. But if you have a little bit of extra money and you're very interested in this, get the original book from Cambridge Press. It's worth it lah. It's really, really good, right? It's got tons of things lah. So the theoretical aspects would be chapter 2, chapter 3, chapter 4. You may look at chapter 4, 5. This could be quite familiar from VLSI for those of you who take under me. Chapter 6 is just like a review of digital electronics, your K-maps. Chapter 7 is starting to look at how you write the Verilog description for combinational logic. And chapter 8 is actually giving you the common combinational logic blocks. And chapter 9, you're looking at complex combinational logic. Chapter 9, chapter 10, chapter 11 are complex. That means they're no longer just simple, what you call a traffic light controller or so they are actually kind of challenging circuits, right? Just to get you to get that. Chapter 12, 13, you can see how people build arithmetic circuits and all that. I'm not going through all of this. I just provide this resource. And frankly speaking, I probably won't test you on this. And I'll tell you why. It used to be about 20 years ago, the key bottleneck in digital systems design, digital circuits, is the computation. That means people were very concerned about how fast can I do arithmetic? Can I do addition, multiplication? How fast can I do logical operation? And and the pinnacle of this type of circuits is the microprocessor. The microprocessor is the most complicated digital circuit focusing on all these kind of designs. But fast forward 20 years now, the bottleneck is no longer computation. In fact, our chips, our digital systems today, they can compute things so fast that it's kind of hard to actually fill up and to keep them busy, right? So you have multi-core. I give you an example. The GPU is the most recent, the best example. You've got like, I think, hundreds to thousands of floating point or fixed point cores. So what I mean by floating point fixed point cores, that's just basically an arithmetic circuit that can do floating point operation or fixed point operation. Right, so fixed point means you're adding fixed point numbers. Floating point means you're adding floating point numbers. We'll talk about that a little bit more a bit later. But I said I'm not going through them because the material are here. If you are stuck, you're not sure, you can ask a question. I can go through it. But apart from that, I probably won't touch it because there's just too many things. These are more traditional material. I assume you will know them. You can pick them up because they're not the main things people work on today. Why? Because if, for example, most of you are from Intel, or if you actually IC design, you will just pull out the arithmetic circuit from a reference design that there's already people have optimized to death, right? It's already very optimal multipliers, adders, and all that. You will just use them. You call them IP core, right? You just copy, use that in your chip. What you spend most of your time doing nowadays is figuring out how do you get the data from one part of the chip to your compute and out from your compute to another part of the chip and so on. So the bottleneck today is your ability to move data around. What do I mean for move data around? Well, you want to take it from memory, you send it to the computation core. Whatever result from the computation core, you want to send it back to memory. Because this is the way we do compute today. It's called the load store architecture. Okay, so most of your time as a digital circuit designer will be spent figuring out how to interface or how to connect computational blocks. So, and memory and storage. So storage and computational blocks, how to figure out how to connect, communicate that, right? So that's why we're going to be paying attention more to the interfaces, right? How is data transmitted from one digital block to another, the timing and all that. And the second important area where you will spend a lot of time is in, let's say you have multiple resources and you want to send data to one to two. That's the problem of synchronization and scheduling. I haven't been able to teach this in this course because students usually can't really get up to that point. But this is the idea where maybe you have 2 or 3 or 4 cores and then you'll be able to figure out how do you actually send data to all of them. And then if you're using or besides multiple cores, you also see the same type of problem in what you call the switches, the network switches, where you are actually able to actually connect from certain one module to another module, and you figure out how you're going to do the connections. Okay, so you'll be spending most of your time designing circuits to do the interfacing and to shuttle data around. That's why I'm not paying so much attention to these combinational circuits, because number one, I've given you the materials, you can read it up, you can design it. B, most likely you will just use it as a black box. There are optimized versions of it. So if you're doing kind of transferring data back and forth, so there is an order, there is a sequence in which things happen. That's why we want to focus on sequential logic, chapter 14. And sequential logic, usually when we talk about it, we have to introduce you to the concept of state. You know all this already, but I'm just going to give you a different spin, a different way of thinking about it, and we'll cover a little bit of that today. In sequential logic, normally if you borrow from this idea from microprocessors, there's a part of the sequential logic that is processing the data, and there's a part that is just focusing on the control. So you have a control path and a data path. So what do I mean by that? I mean, when you have a digital circuit, there's going to be circuits or logic that whose sole purpose is just to figure out what is the current mode of operation of your circuit, right? So because you have a very flexible digital circuit, you can do a lot of things. You can do a multiplication, you can do addition, you can do a shift, many computation operations. So you have to decide, let's say I give you a set of data, which operation you apply. Okay, so that is the control path of it. And then the data path would be, what do you do with the data? So there are generally two sort of parts to a digital logic circuit, the control path and the data path. So that's why it's separate out, the sequential logic here, and the data path for sequential logic, just to give you this idea, this concept that conceptually when we design circuit, we try to be able to identify which is the control and which is the data path. Okay, so this is just throwing out concepts to you. We're not talking about that very detail yet. And then the timing constraints, that's an important part, but we'll come to that later. And then is finite state machines. And what I like about this book is straight away it starts going after the sequential part. It goes into system level design. It gives you an overview by using 3 examples. A game of Pong, how do you play ping pong? There is a computer game, how do you design the logic circuit for it? The DES cracker, this is a circuit that his goal is to crack the DES cryptography method, and a music player. Okay, and this actually gives you an example showing you how to actually partition it and all that. And it covers some advanced circuit technique, which is pipelining. How do you split up circuits so that you don't actually have to wait for everything to be completed? You can actually do part of the computation and then you push it to another part of the circuit, and then you can reuse the resources. That's pipelining. So we may not get into that, but if you're fast enough and you're able to get into that, great. And microcode is just a trick to use memories to implement state machine. Maybe we can cover a little bit of that sometime this semester. Okay, so this is a tremendously good resource, and this is not the complete book. This is an early version. There's a bit of incomplete pages because it's taken from his class notes at Stanford, but you can go ahead and get the textbook if you will. So these are 2 excellent resources for you to really anchor your learning, and the goal is to really get you to learn this well. Okay, what to learn? What able to design and verify digital circuits, complex digital circuits. So the Chu textbook, chapter 4, 5, 6, and the Delhi is a supplementary material. Now, what are these other two textbooks here? For your practical example, like the culmination of this course, the end goal, I have a problem-based learning project. Basically, I would like you to implement this on FPGA. I will give you the access to the FPGA online. Okay, what do you need to do? The idea is very simple. This FPGA, I'm giving you the board documentation, and on this FPGA board, there is an SDRAM chip, synchronous dynamic random access memory, SDRAM. And SDRAM is one of these very complex chips that it's not so easy to read it. It's not like you put the address, you get out the data. No, it's a bit complicated in that. And I have a set of videos that explain to you how the SDRAM, how is that different from your traditional memory. But SDRAM is important to know because I would say it has all the important elements of modern digital systems design, right? Because there is a very fast interface, the way you communicate and send signals. So there's a control signals that you're sending and you're receiving from the SDRAM chip. There's the data path signaling. That means you're either sending data to be stored in the chip or received from the chip. And so you have to really synchronize the control signals and the data path signals, right? And there's a particular sequence in which you send this. So it involves state. And this is really an interface, and the SDRAM actually, if you are a bit advanced, you can actually request memory locations or data from memory in parallel. That means you can actually find ways to speed up the way you retrieve data from an SDRAM. So it's a pretty complicated chip. Yes, I know we don't use SDRAM anymore today. You use DDR RAM. Now I think it's DDR5, double data rate. The key difference between SDRAM and DDR is DDR RAM actually is reading and writing on both the positive edge and negative edge, whereas SDRAM is only on the positive edge or negative. It's a single edge read, right? DDR is doing double edge. Okay, and there are finer differences, but that's the major difference. So even if you were to study and understand SDRAM, you already know how to interface and work with a complex chip. And so the idea here is for you to design a digital circuit and implement an FPGA board so that you can send and write data to the SDRAM and you can retrieve data from the SDRAM. That is the idea. So I've given you the grading rubric. This is how I would actually grade your design. Okay, you can look at this here. Okay, and so this is fairly complex because number one, you sort of need to understand how an SDRAM works. And that's where I've given you this huge book, okay, by Bruce Jacobs. This book covers all kinds of memory systems, okay. And I just want to point you bare minimum, like you can read chapters 7.2, 7.3, 8.1 to 8.8. This is kind of the big picture background about SDRAM, okay. And you read chapter 11 of the Jacobs Specs books to actually just get the idea of how to SDRAM access. After you read these two parts here, you go ahead and read the data sheet. The data sheet is your friend. It tells you everything about how to interface with this. And if you have issues understanding the data sheet and all that, let's discuss that in the session. But I would say the whole course, the summation of it is you develop this design. Everything else is geared up for you to develop this design. This is pretty complex. Okay. Now, for those of you who maybe are a bit allergic to programming, maybe you don't really want to do Verilog, you're just really don't like it. But I recommend just try it first. It's not the same like programming in C or Python or Java, right? The hardware-based programming is quite different. So you cannot write for loops and all that. Although the construct is there, but that's not how the way we write it. There is a particular recipe, and I hope to impress on you to go over with you so that you understand how it works and the recipe, and then you will see it's quite straightforward. But if you really decide you don't want to do this, there's always the option for you design by hand. That is the idea of using lookup tables. Okay, and I'll go through that a little bit more. So you have that idea, that you have that option as the last resort. It's quite a bit more tedious than doing with the code, the Verilog code, but you will understand digital circuits like nothing else. Okay, so you understand it very well. So here I've given you some background material on SDRAM and FPGA, plus I've got two previous lectures I've recorded. This is actually introducing FPGAs, and this is actually introducing SDRAM control and interfacing. This one is also another follow-up on the DRAM systems, all that. Okay, right. So that's the big picture. Okay, I've still to decide a few other assignments to give you, but I don't want to add too much lah, because this one is pretty big already. The other assignments, if I were to give you, is more of just to move you along so that you don't keep this to the last, because digital circuit design, you get good at it by practicing. So you have to design a lot and you think about it and you have to just design and design and design. So there are a bunch of exercises from the book and all that that I can give you, but I think at this moment, I just want to see how far you can get. So if you just want to get some extra references on memory-based systems, you can read these sections. These are just giving you kind of like a big block diagram. In the earlier days, I actually had some code to do different parts of this, but I'm not doing this anymore. But if you like, you want to have a look at this code, I don't mind to share with you. And this is the idea that DRAM itself, you have the row access and the column access. And then the idea of SDRAM is, instead of actually putting in an address, right, you try to clock it. And then internally in the SDRAM itself, you can just specify a base address and then how many words, how many memory locations you want to read. Internally, there'll be a counter that will increment and really fetch the entire DRAM, maybe a set of 8 words or 4 words from the DRAM directly. And what is nice about this is actually you can actually tile DRAM banks in parallel, so that if you're reading one element from here or a few elements from here while it's still processing this, you can make another request from this. And I said in the old days, I actually had a crossbar switch design here, simple one, 1 to 2, where you can actually figure out whether you're choosing to access the first DRAM or the second, and then you have a scheduler to figure out how you want to connect, and then you have a FIFO. So this is the picture of how complicated this whole thing can be, right? It's got all the main elements of modern digital systems design. You've got a synchronization device, the FIFO. You've got a scheduler, resource allocation. You've got crossbar, which is a fancy interconnect. You've got parallelization, bit slicing, and all that. But this seemed to be a bit too complicated for most students. So I'm just having this here is a resource. If you think you're interested to look at it, I can share with you the base Verilog code. But nowadays, I'm teaching it a little bit differently. I just focus on you are designing to read and write from the SDRAM. And I like to actually anchor it on the textbook, the true textbook, chapters 4, 5, 6. And then you use the DARI textbook. And then we see what kind of example problems you can work on in increasing order of complexity until you're ready to design this. But don't wait until the last minute. Take a look at this immediately and try to get a sense of it. So at least you don't get too surprised, because it's not an easy problem. But the good news is if you can do this, I actually have it on good word from the Intel architects that it actually puts you in a good situation with your seniors or the people who are actually in IC design. You're actually quite prepared to do a complex design already. So further on that, I'll mention that the tools we are using. So in this course, I'm using purely open source tools. I understand that maybe in your IC design environment, you will have maybe Cadence or other tools like that. That's okay. You can use that. And then the key part is, you just have syntax differences, but those tools are kind of expensive, and I've put together the flow. You actually have for this front level, like front end design, this is called front end design. You would only need a Verilog synthesizer and a simulator. Synthesizers means whatever Verilog code you write, it will map it into discrete logic gates. Basically, those who took VLSI, it will map it into your design library, your .lib file for ASIC. And if you learn in FPGA, there's an equivalent in FPGA. It's called the FPGA blocks, the configurer logic blocks and all that. So FPGA has its own unique kind of basic circuit elements, right? But they are somewhat different from the the ASIC ones. The ASIC one, you have your non-NAND gate, NOR gate, you have your multiplexer and all that. FPGA, you don't. FPGA, you'll find that if you go through my introduction video plus you read this paper, very recent paper on FPGAs, you find that FPGAs actually don't have logic gates. They actually have lookup tables, or it's actually a form of memory lah, and you implement logic gates that way. So it's a bunch of memories interconnected by crossbar switches, and then what you do is you actually program by implementing a lookup table in the memory, and then selecting the connectivity of the crossbar switches. Okay, more on that later. If you don't quite understand what I said that, you can write it down, ask me later, but I also hope to cover it. Okay. But it's just to give you a big picture that the tools are here. There's a simulator and there's a synthesis tool. You can just download Docker. Docker is a container, virtual machine container. You can download it onto your laptop, and you can just run it. The simulator is there. We are using Icarus Verilog, which the website I've listed here. You don't actually have to use this, but if you are a bit allergic to setting this up, you can also go to the online simulator at EDA Playground, and this is what it looks like. This is what it looks like. So I've got a bunch of example designs here. So here is again that SDRAM crossbar example, where here is actually your design. You write your Verilog code design here, and here's your test bench. Test bench is basically you need to actually verify that whatever you describe here, your design, is it working or not. So the test bench is basically you are setting signals up and down. It's like basically your function generator. So this is like you're writing a function generator to put in signals here, and then you're measuring it. And then you can go ahead and just run this, and then you simulate it, and then you can actually download the visual the file, or you can actually read the kind of the timing diagrams here. So these are timing diagrams. These are all the signals that I pull out. This is the ones and zeros, and you can check your design this way. And for those of you who are familiar, this file, I forgot what this file is. I think it's a you actually have the option to actually download it. You can download the files and run it. So you can actually download it and view it on your local machine viewer if you so wish. But this, I'm just sharing you, this tool is fully available. You can access this simulator online, and you can choose again a whole bunch of simulators to use lah. I just try to stick to Icarus Verilog, and I run through this in the design here, in the example here. I run through a little bit how to set it up and use it. But if you have any questions how to use the software, let me know. Okay, so this is all jumping ahead of the game. We've not actually started talking about what this is, although I hope you actually have started looking at the textbook and studying. I'm just showing you the big picture. What are we going to cover? Really, the focus is on you to be able to do complex digital systems design, complex digital circuit design. How you're really going to design the circuit, and you're really going to describe the circuit. And Chu textbook, Delhi textbook will be your basic guide, how to really pick up the circuit design and the coding. And where you're ultimately going is to this problem-based learning project. You're going to design your own circuit to read and write from a real SDRAM chip, and you implement it on FPGA. Okay, that's where we're going. There are some background material on SDRAM, FPGA. You can learn that at your own level, at your own time. And there's also software for you to actually design and validate your design. Okay, now let's jump into the actual work. Okay, the actual parts. Practical module 1, I'm giving you examples, basic examples of what a Verilog code and what a test bench look like. Okay, and there's specific reasons why I give you these 3 circuits. An adder is the most basic example, not so simple, but it's not very complicated. It's an example of a complex combinational circuit. Okay, so I think this is a 4-bit adder, right? How you add 2 numbers together. So if you actually go through it, there is a design and there's a test bench. So you can actually just literally open this system Verilog file. You paste the design part here, the test bench part here, you click run, and you can go line by line to understand how the design is done and how the test bench is done. Because the test bench, as I say, is nothing else but a logic, like a function generator. So you're actually specifying the functions, when you're going to go logic 1, logic 0, how many inputs, outputs you can do. Okay, the multiplexer, I give you a multiplexer, so because it's a simpler form of a logic circuit, but I like to tell you about multiplexers because I will show you hopefully today. You can actually design logic circuits only using multiplexers. You don't need to use AND or NOT gates, right? Purely based on multiplexers, you can do it. And what's nice about that is it helps you to think about it as a input to output mapping problem, and it takes you away from this idea that I have to write K-maps, because I'm trying to undo that part of digital electronics training that you've gone through. You understand, because that part of digital electronics is just basically saying I need this function. How do I implement it? I need to implement it in discrete gates. So I get the discrete ICs, the IC with the AND gate, the OR gate. But here, you're talking about digital circuits. Basically, you have to understand that combinational logic is nothing else but an input and output mapping. You have many ways to implement it. You don't have to implement with AND OR gates. You can implement purely multiplexers. You can implement purely with even lookup tables, which are nothing else but maybe a kind of ROM or SRAM. You can do that. And that's actually how it's done in the FPGA. That's why I like to suggest this, because if you have the multiplexer approach for designing circuits, writing the Verilog becomes almost like a recipe already. You don't actually have to think very much hard about writing the Verilog. It's sort of like, you know, how McDonald's is able to make great burgers because they're able to have a recipe that any franchise can open. Yeah, so if you can frame your circuit as a multiplexer or lookup table way of doing it, the Verilog is almost just like a recipe. You just follow it, you fill in the blanks, you know how to design it. Okay, that's why I'm going to focus a lot on the multiplexer and lookup table approach to designing digital circuits. Okay, and the counter example is just this basic, most simple example of how you are going to design a sequential circuit. All right. I've talked a lot so far already, and I've been jumping around all over the place because I'm trying to give you an overview, a big picture. I don't expect you to understand everything, but at least roughly half of it should sound a bit familiar lah. And I'm going to take a pause now to check if you have any questions. And if you don't have any questions, after this, we're going to start diving deep. I'm going to anchor you on digital design and going to introduce you to both combinational and sequential design. But from a different perspective, and we're going to move a little bit faster. It's not for a fundamental class. I'm not going to review it. I'm going to just give you a different way to do this design. All right. So any questions so far? Anything that was not quite clear?
Not at the moment, Doctor.
Not at the moment.
But do we have any additional online references that we can refer to?
Online references, you mean examples and all that? I think just it, right? I think this book is already chock full of examples. This book also is chock full of examples. What I mean by chock full is you would have at least 4 to 5 full combinational as well as sequential circuits, fully designed for you, with the step-by-step describing what they are with the Verilog code. So between these two books, actually is really a lot already. I don't even know if you can go through all of them. But if you still need more, then let me know lah. Okay, but I think between these two books, the Chu book and the Delhi book, plenty of examples already there. And then you can also go through this. Okay. So I actually don't think you need to go online, because these two books, actually, they've got pretty good examples, right? You try to take a look at it and see, and you know, if it doesn't really satisfy you or it's too complex and all that, at the moment, you give me a WhatsApp in the group, and then we'll see how to help you solve your difficulty. But I think you don't actually need to go online. You can focus on this book and this book. They've got plenty of really, really good examples. And I add this book. I forgot to tell you about this book. This book is because if we have time, I would like to give you some high-level approach how to estimate the throughput of the communication link. Yeah, because when later on we'll cover when you do communication, there's packets that you send, there are headers and all that. So there is an overhead to that. This book actually, there's certain chapters, I think 3 and 5, will give you some high-level equations. You can more or less know how much data or how much throughput you can can push this through lah. And this is good for high level design. But if we have time lah, my focus is still on you to be able to design complex digital circuit lah. All right. Okay, more questions? If not, I'll move on.
Dr. Mukesh here.
Yes, Mukesh.
Yeah, how many PBL projects we have for this subject? Just one or there have been
Okay,
like
Mukesh, great question. In this course, I'm only going to give you this one PBL project, but I may give you some additional smaller textbook questions or additional design question lah. So the PBL one is really the culmination lah. If you can do the PBL, actually I don't need to test you on anything else because this is pretty complex. So there's only one PBL. The rest I haven't really figured out because I want to see how you all are progressing with the learning. And if I give you other assignment, it's only just to kind of to nudge you to learn it and not keep it to the last minute lah. It's more of just to help you to gain marks for the course lah. But really, I'm just more or less interested in the PBL lah.
okay.
Okay, so it's not going to be so heavy like VLSI. I had like 2 PBL and then like 4 homework questions. It's not going to be that heavy because I actually want you to spend more time on learning the design. But I will try to track you on a closer basis lah, maybe every week just to check how you guys are doing lah. Because I think there's a tendency all of you are very busy. You may not be able to spend that much time on this, but that's what makes me afraid lah, because if you spend 1-2 weeks revising and you hope to do the PBL, you're not going to be able to make it. I guarantee you, cannot. And you have to cross a certain learning threshold lah. The learning curve is a little bit steep. Once you cross that threshold where you know you can be able to design your own sequential circuits and you can see how it's doing to do it, the PBL is going to be straightforward. But it's a little bit of a pain to cross that, and I'm still finding the best recipe to help you to cross it lah. So far, the better approach I know is you have to study these chapters and look at the examples. That's a starting point. And somehow I need to give you some intermediate, not too easy toy problems. That's why I don't like traffic light control, because it's too easy. Always students do the traffic light controllers, then after that say, I don't know how to do anything else, right? So it's too easy. It's not realistic enough. So maybe I just walk through some examples today. We will just look at it from different perspectives, and then we'll see if you guys if you can look at the problem chapters here. I've also identified some problems that you could actually do from the textbooks, but I kind of want to see how your learning goes in the first week and a half to 2 weeks first now, and whether you all can pick it up without too much of work pressure lah, like homework pressure, I don't know, does that make sense? Because the best thing actually would be if you look at parts of these and then you start even designing parts of these lah. But let's see how it goes lah. Let me know if you can finish these chapters and if you're able to do some of the homework questions at the back lah. But like I said, the target is you must complete all of this in the next 2, maximum 3 weeks. You must learn all of this, right? Chapters 4, 5, 6, the sequential logic. If you don't, you're out of time, because you really need that long to actually figure out how to do the design.
So the deadline, I saw is 31st October. Is that a hard deadline or?
This one, well, you know me lah. I'm a little bit flexible. I try to give you a moving deadline, but not too much lah. Also last semester, it reinforced my view lah that the moving deadline actually, it helps in some way. You don't feel so pressured, but it also allows you to push the learning too late into the semester, and then you're not able to really pick up some of the material lah. So that's my worry lah. So try to hit 31st October, but if you can't, then we'll see lah. You'll bleed into November and all that lah. But I mean, at the very latest, you should be like before December lah, right? Because it does take a long time actually. So this is just kind of to, give you some urgency lah, that maybe you should think about starting this thing in the beginning of October, something like that lah.
Okay, sure.
Okay. Yeah, I'm still flexible, but I don't want you to think like this is a very loose deadline, because I'll give you a point of comparison lah. Like VLSI, last semester, that one actually is a bit of a mugging subject. So if you put your mind to it, you spend a certain number of hours, you'll get it. This one is not like that. This one is design. There's no way to teach you design until you do it. And the best way to teach you design is you do it, and then you come to the weekly meeting or the bi-weekly meeting and you say, I really can't get over this. Show me. Then I can show you. Right? Because again, all the examples are in the Chu textbook, the Delhi textbook. They're in between them, 8 to 9 fully worked out examples. If you need more, there's more, right? You can go as complex as entire microprocessor designs, like the MIPS design, the RISC-V design. You can even look at all of those, no problem. But how much time do you have? And do you have the stomach to actually go through all of that? I think we may not need to go through the microprocessor. We can actually stick to this. But if you're really, really interested and you want to take a look at that, well, those of you who had done VLSI with me last semester, you've got the RISC-V. You can take a look at it, parts of it. And if there are parts that you don't understand, we can also bring and discuss the design here, and I can show you how it's done. Because one of the things I actually want you to get is I want you to look at Verilog and the actual circuit. Like those things are interchangeable. You must be able to just read the Verilog and just sketch and draw the circuit block directly. That's the level of proficiency ultimately you should have. Then you can be a good digital circuit designer. And it's not impossible. If you actually take the lookup table and the multiplexer approach to designing circuits, it's actually quite straightforward. It's not that difficult. It's almost as if you can write a pseudocode and then you can draw out the circuit already. I'll show you how. That's part of today, that introduction. But let's see if we can get to it. If we can't, then I have to bleed over into the next session because increasingly I have realized over the years, I have to ground you in what I call problem specification. You have to specify the problem first, because a lot of you get confused. You start straight away going in and then you start wanting to design the circuit and do K-maps and all that, but you miss a very important step, which is specifying the problem. And that's what I want to cover today. Okay, more questions? If not, I can start.
Last question.
Yeah, please.
Yeah, so this assignment is about coding in FPGA, right? So is there any FPGA environment for us to use?
Yes, Gabriel. Excellent. Intel is very kind. Intel has actually this what called system cloud for university and we are one of the first people to try it out I got 4 accounts last semester for 4 students. I'm going to request this again. And what this is nice is really Intel has just come up with a system where you will log into a cloud system. Okay, and that cloud system, nothing else but you just get into one of the PCs sitting in the Intel lab. And that PC has an FPGA connected to it. And you can actually look at the FPGA, you can program it directly. And if you need certain pins connected to a logic analyzer, you can do all of that. So there is already a setup where you can actually test this on FPGA at a distance, right? So I plan to use that. Okay, so I'm going to be requesting accounts for all of you. I don't know how many they'll give, but I think we can also share. And if it really becomes push comes to shove, then we can actually maybe schedule it among ourselves. At the moment, I don't think many people are using that system. It's a bit idling, but I really want to push you all to use it. So it's like, yeah, you can actually just, it's as if that system is in such a way that you just log into some account that's got some VPN and all that. Then you just see the Windows desktop on it, and then it's as if you're working on the computer connected to the FPGA. Yeah, and you can actually see the FPGA. So yes, we do have that, courtesy of Intel. Yes.
So may I know when will we get this infrastructure?
Okay.
To us? Yeah.
I will write to them next week because I think this was down for maintenance up to 4th of October. I'll write to them next week. So I would anticipate by middle of October, you already should have it. But that should not be something to really stop you because there's quite a lot of work in terms of writing the register transfer logic, ITL code, which is People say RTL code, that's interchangeable word for Verilog code lah, or VHDL code. But in this class, I teach Verilog lah. VHDL, I'm not so familiar with the syntax. I think most design houses would use Verilog here lah. But if you really want to use VHDL, let's chit chat a little bit lah. Okay. Yeah.
Yeah, just now you mentioned we are using the Verilog, but the book you are suggest to us is using the system Verilog. So which one should we use actually?
Okay, Yaking, let me clarify this. That's a great question. System Verilog is a newer version of the Verilog standard lah. Okay, there's just certain additional keywords, and one thing is very powerful about System Verilog is the testing setup, the testing and verification setup. The way you can write test benches, it's got a lot of extra syntax for assertions, assertion checking, and as well as transaction-based kind of checking. So System Verilog really, I think, is compliant with the OVM and UVM testing methodology. That one, I don't know if Dr. Famizu will cover in the system test and verification, but System Verilog mostly is about that. And I think you will also observe the true textbook is teaching you System Verilog, meaning it's got some advanced features that not really in regular Verilog. My take on this is like this. Whether you write it in the advanced System Verilog or just in Verilog, as long as the compiler and the FPGA compiler can take it, I don't care because the syntax is not really that difficult. It's just a little bit more shortcuts only. I just teach Verilog because I've not found it necessary to use System Verilog so far. I think the strength of System Verilog is in the testing infrastructure. Because what do I mean by testing infrastructure? Well, I said the very simple way to think about testing and verification is you have a test bench, right? A test bench is nothing else but a function generator. So you create functions and you can specify every input pin, what is the logic 1 and 0, and when is it going to logic 1, when is it going to logic 0, and then you read the output pins from your design and you can check all of that. System Verilog makes it a little bit simpler because of something called the assertion checking is important. Assertion is basically you are having this sort of mid to high level kind of I wouldn't say command, but conditions where the Verilog simulator will check, is there any way that these conditions will be violated by your current design? So this is useful when you actually have very complicated designs, or when you expect that, when you're writing this kind of logic, you are actually figuring out that, it has to behave only in this way. And this is the reason why I'm actually trying to move you away from K-maps and all that. It's because modern digital designs are so complex, you really shouldn't be paying attention to how to draw the logic gates, because that's done for you by the synthesis tool. But I've always found it helpful. It's still good if you can actually see this particular logic, this capture Verilog code can map into what kind of discrete logic. And again, I'll show you how it's done. If you can see that, it will actually help you to build better design. So I hope I answer your question. Yaking is kind of the same language. It's just that System Verilog have extra syntax that maybe make things a little bit shortcut. I think I've observed one of them is the way you define the system clock, like for the behavioral RTL side. So always add, they put always at hash or something, but the older Verilog, you either have to put a pause H and then there's a clock signal, or you just put a normal signal and then that becomes sensitivity list. Okay, so it's just additional syntax in terms of the synthesis part. But if you use one or the other, I'm not fussy, because at the end of the day, if this is synthesizable, it's simulated and it's correct, no problem. You actually should be updated. You should pick up System Verilog because you guys are young. I'm a little bit old already and I've not found it useful enough. But like I said, the advantage is really in the assertions. There's very, very powerful syntax for you to specify all kind of assertions. It can tell you to look for patterns where there are like 1 transitions, 2 transitions without even specifying any kind of timing in between. This is the example of how powerful it is. I can share with you again a book on verification that's got lots of assertions. You just remind me, I can forward it to you guys on the private side. So that's one. And the second is the UVM or OVM infrastructure in system Verilog. You can actually specify transactions lah. So what is a transaction? It's a high level concept where if you think about I'm transferring data, right? I'm no longer just sending bits or ones and zero. You have header, you have header, you have data packet, and then there are random sets of these packets going through the communication line. So a transaction is actually one set of these like packets going through lah. And the system Verilog, if you really know how to use it, you can actually create like, random kind of generated packets and all these kind of things with different header, different packet size and all that lah. Transaction level simulations lah. So I said the strength really, from my understanding, is on the test and verification methodology lah. Yeah. Is that okay? Yeah, okay.
Yeah, sure.
Okay. Anything else? Okay, great. If not, then let me jump in and talk about what I actually wanted to cover today lah. And I said I want to spend a little bit of time talking about specifications, right? Okay. Normally, if I tell you lah, okay, let's start with maybe a basic design lah. I want to design, let's say I want to design a system, simple alarm system for the car. There's your undergraduate example, right? Alarm system for a car. Okay, if the door is open and the key is in the engine, sound the alarm. If the door is closed and the key is in the engine, don't sound the alarm. If the key is in the engine, if the door is closed, key is not in the engine, lock is open, sound the alarm, something like that, right? So we are quite used to this kind of specification from undergraduate, and then you straight away will just draw the truth table, right? Correct? That is quite familiar to you, right? So if you say you draw the truth table, you actually insert, let me insert table. You have something like this, look. So then you will define your inputs and your inputs. Okay, so you got input, you got maybe bit 1. So you got input bit 2, and you got input bit 3. Okay, then you got output 1, then you got output. Okay, let me just define a proper example. Okay, okay, insert text box. So I've said, let's say you want to design a car alarm system. Okay, so the inputs are key in ignition or not, safety belt are fastened or not, engine on or not, doors open or shut. Okay, right. Okay, so you got a problem specification like this. Okay, then straight away you say, okay, maybe it looks like I can have 4 inputs and 1 output lah. 1 output A. So the output is the alarm lah. Logic 1 means alarm sound, logic 0 means alarm don't sound. And you can also simply define lah. Input A, if the key is in the ignition, is logic 1, key is not in ignition, logic 0. So you can actually specify 0, you can actually specify lah all the combinations of inputs like this. Etc. lah. And then you go in the situation like this. Okay, key is not in the ignition, so not means it's 0 lah. Okay, not means it's logic 0. Not means it's logic 0. Means it's logic 0. Okay, so key in the ignition is not in the ignition. Safety belt is not fastened. Engine is not on. Doors are shut. Okay, so here doors are shut, no alarm lah. Okay, D doors are open. Okay, doors are open. Maybe I want to have an alarm so that just to tell me to shut the door lah. And then here input C, the engine is on, door is shut, safety belt not fastened, key is not in the ignition. So this is weird because this should not happen. So I can put a don't care. Okay, so I think this process is quite familiar to you, right? Am I right? This is combinational circuit design. Is this familiar to you?
Yeah, I mean.
Okay, great. Now, let me tell you why I think this is a problem. You will go through this and you will expect that everything is laid out so clearly, like your sensors is so clearly laid out, your inputs is so clearly laid out, and you just put all of this here, right? And then your focus actually is you just want to fill up this table so you can draw Kano map, and then you can figure out output A. I draw a Kano map with 4 inputs, then for output A, how to generate the digital logic, correct? And you will spend, I would say, 80% of your time solving the Kano map to find the digital logic for output A. Am I correct? But that's not where you should spend most of your time. You should actually spend most of your time in defining this table. And I'll give you an example why. This table is called the truth table, but you need to look at this table as the agreement of what your circuit is doing. I would say it is the specification. Why? Because at the end of the day, this table is just saying that it's a black box. This black box is called digital circuit. Okay. Circuit is doing is I'm going to specify I'm taking in 4 inputs. And 1 output, right? I'm going to specify that. This table and this black box, same, except that this table is telling me all the possible conditions on the input and what the output must respond to this, okay? So the key fact that you have to pay attention to in the digital systems design part is, do you understand that this truth table is actually specifying the requirements of your design? This is the most important part. It is not solving the K-maps. So please, whenever you start in this course, stop trying to solve K-maps, stop trying to rush through this process, because the most important part is here. And as I'll show you in the next example, where we're going to do an example how to design a password system, okay, a password keypad lock system. There are multiple ways to define the inputs. It's not always clear, and you should actually spend a lot of time to think about how you're going to do that. And this, plus you almost never see this kind of situation, right? Because this kind of situation, there's no sequence, right? It's just like the thing is on or off, right? And then I really can point out a flaw here. This is a poorly conceived design. Why? Because again, output D, the door is open, and then I want to set the alarm. It's not likely that I'll get an alarm when the door is open and key is not in the ignition, safety back not, entry or not. I will get the alarm if the door is open for a certain amount of time, let's say 5 minutes or 10 minutes, correct? If the door is immediately open, I won't have. So you see these kind of toy problems, A, they're not very useful. B, you will almost always find some way where if you specify in this way, it's not satisfactory. Why? Because there needs to be an element of time, of sequence to make designs useful. So here, like I said, this part here, this branch here, as we've reasoned out, it's not very useful because this one, if you implement this logic, the minute you open the door, after you shut the engine, everything, your car stop, the minute you open the door, the alarm will sound. So it's not useful. What you actually want is the alarm will sound, the alarm will be 0 if time open less than maybe, let's say, 5 minutes. You want if time open greater than 5 minutes. You want something like this, right? Yeah, this is more useful than the previous specification, right? Do you follow me? Is that helpful?
Yeah.
Okay, so good, because the idea I want to get here, the big picture idea before we go into all the details, because this is design, you don't really follow a recipe, although I try to make it as much of a recipe as I can. You have to spend time thinking. There are multiple ways for you to define the inputs. There are multiple ways for you to define the outputs, right? And don't be in a rush to just get the first one that comes to your mind. Try to think if there are alternative ways to do it, because that's where you get most of the simplification and the elegance. The second concept I need you to understand is that the reason you specify a truth table is because you want to ensure that for all possible input cases, you define the output completely. You know why? You want to avoid the case where you haven't considered a particular input situation and then the output becomes something else, right? So this is a case where there's undefined output, and it's not like your circuit is not going to send an output. Your circuit is actually going to get an output, because if you only were to consider certain parts of this circuit, those conditions which you never considered about the input, they will be a don't care, and then your particular implementation or the solver or the synthesis will assume some kind of output, right? And what I'm worried about is if you don't figure out and really comprehensively understand all the possible input combinations, and the output has to be specified for all those combinations, you may actually get, for some unplanned input combination, your output leads to some kind of catastrophic failure lah. My favorite example is if you're designing circuit for, let's say, a pacemaker or something like that. If you fail to take care of the don't cares and all that, you will probably kill somebody lah. Okay, so the first point is you have to spend some time thinking about this table. This table is not just a table for you to do K-maps. This is actually your specification, your agreement, how your circuit, what is your circuit actually going to do? Because the user doesn't actually care about what's inside here. You are going to be designing what's inside here. You are going to be designing the algorithm here, but the user cares about, if I put a bunch of inputs here, okay, what is the output that I will get, right? The behavior is what the user cares about. Right, so here this truth table is only telling you static. If I just put one pattern here, I get something. But later on in sequential circuits, which is the bulk of the case, what you care about is I'm going to put a sequence of input patterns, and I'm going to generate a sequence of output patterns. That's what makes digital systems or digital circuits complicated. So you follow me? So we have to find a way to specify how are we going to specify this sequence of inputs lead to a sequence of outputs. That is the specification of your digital system. Okay, can? Okay, maybe still a bit unclear lah. So let me give you another example. We go through a work example. So your example is design a safety lock system, right? It's a digital system implementing a passcode lah. Okay, so you can think that your input is 10 value keypad, 10 number keypad, sorry. Okay, so you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 10 numbers, right? So you have to design a system in such a way that if the person press the correct sequence of password, the lock is unlocked. Otherwise, it is not unlocked. Okay, right. I throw it back to you now. How are you going to design this? What is the specification? We start with this black box. What are your inputs? What are your outputs? Can I get some suggestions, some thoughts?
Input is 0 to 9, output is
0
unlocked.
to 9. Okay, great. So the one suggestion that you have inputs and output is 1 unlock. Okay, so this one, okay, I will just use my own way of doing it. Normally you put a cross dash on it. Okay, is that the only way we can define the number of input and outputs? Can you think of another way we might define the input and outputs? How many inputs do you actually need? What is the minimum number of inputs you need? 10? What do you think? You do less than 10 input.
This is a bit width, is it?
Is a bit width, correct?
So it should be around 3 bits.
3 bits. Why 3 bits?
So 1, 2, 4. Right. 4 bits, sorry.
Okay, great. So there's another approach, which is you want to only use 4 bits. Okay. Now I've got options. My first option is I have 10 input signals. Second option is I've got 4 input signals. Is that the only way you can encode this? What other ways can I encode this? Okay, great. So now we talk about encoding. This is one of the important concepts you have to consider. A digital bit or a signal does not have a meaning. You as the designer assign the meaning. Okay, so when you specify the design, so what I mean by specify, you're not giving the implementation of design. There are two parts. One is specify the design, and second is you actually show the implementation. So there are two parts in the design process. Okay, so we are now in the process of specification because, as I said, most of the time the customer will just tell you something like this. Okay, the customer will just tell you something like this, do this, but there are several different ways that you can actually specify this design. So the interface is important. So one of the aspects of it is the encoding. What kind of meaning do you want to assign to the input signals? Okay, so or the output signals, right? So if your specification has to be will be complete if A, number one. Okay, this is the block you need to design. Sometimes you will see it will be called DUT lah, which is actually stands for device under test lah. This is the test bench, right? This is the box you want to design, your digital circuit. The first thing you have to figure out is what are the input signals, what are the output signals? How many lines in, how many lines out? And the reason you need to do that is because you have to ensure that you know the complete behavior for all possible input combinations. You know the complete behavior of the output. Okay, not just for one instance, but for all possible sequences. And I cannot emphasize to you how important that is. So the first step is you need to figure out how many input and output signals. Okay, and part of that goes to the question of encoding. So if you go for step one, where you have 10 signals, you're actually using what they call the one hot encoding. Okay, one hot encoding, you have one bit basically on or off for any of these keys. Okay, so I am able to have 10 keys, so one bit for each key. So I have let's say key indexed by 0, that is key 0 lah. So logic, so I can put logic 0 means key not press, logic 1 means key press. Okay. Right. Second option I have is 4 input signals, right? I look at the array like this, right? 4 input signals, I've actually more than one way to encode it. I can encode it as a fixed point integer. That means if I press this key 0, I will get maybe 0, 0, 0 lah. Okay. If I press this key, I will get 0, 0, 0, 0, 0. I press this key, I get 0, 0, 0, 1. I press this key, get 0, 0, 1, 0. I press this key, I get 0, 0, 1, 1, and so on. So I can actually encode it as a fixed point integer. I can also encode it as a row column format, right? Where I will say this, if it lies in this row, it's going to be, the value is going to be 1. If it lies in a row, the value is going to be 2. If it lies in a row, the value is going to be 3. Okay. So in this case, I have a mapping table. So I just say row LSB, column LSB, column LSB. This is key 0, and all that. So if I press key 0, the row LSB is going to be 1. It's because it's on column 1 and row 1, and column LSB also going to be 1. If I press key 1, I'm at the first row, second column. So second column, this will be like that. First row. If I press key 2, I'm in the first row, third column. Third column, first row. If I press key 3, I'm in the second row, first column. Be 1, 0. Okay, and so on. So this is one encoding if I'm only going to use 4 keys. And there's also a second encoding, which I can use the binary digits. I would say 0 is something like this. Here you see already, just by this simple example, I've already given you 3 ways that I can encode my inputs. All right. So I have already 3 ways where I can actually define a system. And if I keep thinking about this, there's probably almost an unlimited number of ways I can design this system. Okay. And each will have its pros and cons. But my key point to tell you this is, you as the designer, number one, need to specify how many inputs, what do they mean? And your specification is not complete until you tell me or you document what does every single bit mean. So here as an example, 0 is key not pressed, 1 is key pressed, or this is the mapping table. This is not a truth table, right? Don't get confused that a table is a truth table. A truth table is just the relationship between input signal and output signal. That's a truth table. That gives you the relationship, the black box, or you can think about it as a function, right? You put in some inputs, you get an output out, right? So the truth table is actually telling you all the possible values the function can return to you, right? This is just an encoding, a mapping, just telling you that this is what this key, this set of numbers actually means this key. This set of bits actually mean this key. You have to specify the encoding exactly. Otherwise, design not complete. The specification not complete. And if you fail at this step, you're going to get a nightmare at the implementation stage. And this is where most students fail. They skip this step, or they make some crazy assumptions and they don't really list this out, okay? And then they go into the design, and then I don't know what design comes out. It doesn't really work because you've not actually agreed on this. So again, is this a complete specification? No, because all we've done is we specified the number of inputs, the recent number of outputs, and the encoding. We haven't said anything about how many keys in a passcode. So how many keys do you think should be in this passcode? Like, is 1 key enough? That means I only press either 0 or 1 or 2 or 3 or 4 or 5, then the lock open. Do you think that's sufficient? Do you think that's good enough? Okay, never mind, I'll just push it along. Probably not, because it's a passcode. Nobody has a single digit pin, right? So they will have multi-digit pins. So you will need, let's say, at least 4 digits in sequence. Okay, so the user has not just had to press one of these numbers and then this thing unlocks. There has to be a sequence of numbers, then this unlocked, correct? So somehow your digital circuit must be able to remember the sequence of numbers. So how do I specify in my specification this sequence of numbers? It's a little bit tricky, isn't it? Okay, so we're not going to actually say so much yet. We're just going to try to fiddle our way around to see if we can arrive at the answer lah. Okay, so the first thing is I would say, okay, perhaps there is some arbitrary passcode. Okay, let's say I said the passcode. What is the passcode? I want to say 4 digits, open when user enters 5606. Okay, right? So I would say, okay, what does that mean? I need to enter 5, number 5. Then I need to enter 6, to enter 0. And then I need to enter 6. Okay. And then I'm going to draw arrows connecting them so that you know that it is actually in a sequence lah. I have to enter them in a sequence. And only after this, I unlock. Okay. Now, is this a complete specification? Do you think it's a complete specification now? What else is missing? Or is complete? I have my input encoding. I can choose either one hot or either of these two encoding. And then now I'm saying that I need somehow to go through this sequence of numbers, then only unlock. Is this a complete specification of my design? And there again, like I said, we have not done any design yet. We are just defining what the circuit must do. Specification. Do you think this is complete?
If let's say the user enters wrong number, then you have to go back the first bubble.
Okay, so interesting point. Gabriel has mentioned, I've only given the correct sequence. I've not specified what happens in the wrong sequences. So if I don't specify, maybe it will unlock on the wrong sequence. So I need another specification. You need to say every other sequence is right. And then you raise another important point. What happens after the sequence and how do you start the sequence? Okay, right? I have a sequence of 4. Okay, what is the sequence? If I do 4, 5, 6, or 6, will it unlock? Okay, now I'm walking through you the process of actually specifying a design so that you realize the things you have to take into account and you have to state it, right? So previously we said, okay, this is a sequence where I unlock. Every other sequence, it remains locked, okay? Right? So actually what we're actually saying is, again, like you said, at this point, you've not actually specified the output. You only specified the output at this point. So actually, in order to specify the output, you have to say lock at every point, right? So now it's getting more complete. But in this case, every time you specify a sequence of 4 numbers, if it's this particular sequence, it will unlock. If it's some other sequence, it will just remain locked. Okay. But after this sequence, what happens? You have to reconsider again. But there's also the possibility where you said, I don't care, as long as the last 4 digits is this, it will open. So will this unlock or not? Right? So I could actually have could also have these are possible sequence. This is a sequence of 4 numbers, 5 numbers. This is a sequence of 6 numbers. This is a sequence of 8 numbers. Okay, so in which of these cases will it unlock? Okay, so if you consider normal house alarm, the cheap one lah, it will unlock here only. And if the less cheap, the not so cheap one, maybe this one, but most of the time here it will stay locked lah, right? Because it will assume you input this number, okay, and then this number is incomplete input lah. All right. So you see with this example, what I'm trying to show you is something as simple as this. You take for granted. There are many things and many ways the design could evolve. And if you don't specify it, your synthesis tool will make the decision for you and you actually have no control and you don't know what's happening, right? It could be that you intended this to be the behavior, but if you don't specify it, maybe the synthesis tool will just make this to be true. So if you want this to be the behavior, you somehow has to say that after every sequence of 4 numbers, start or reconsider the sequence again. So this statement means I will do this. Or you can say the alternative will be just evaluate the last 4 digits of any arbitrary sequence. Okay, in that case, this one will unlock, this one also will unlock. You see, so depending on whether you choose this first condition or this second condition will lead to a different behavior. The first condition, this sequence will be locked, this sequence will be unlocked, and this sequence will be locked. If you choose the second condition, yes.
Sorry,
Yes.
just to sorry for interrupt.
Sure, go
what,
ahead.
yeah,
Yeah.
what if the condition that usually when we enter the coding, right?
Yes.
We have like confirmation return or confirmation input such as hash key or return something like that.
Great, great, good, Lukman. That is an option for you. Do we need to enter a confirmation pin, a confirmation key? So that's an open question. So if you want to enter a confirmation key, then what you're saying is you evaluate the pin only after the confirmation key has been entered. That means I need to add one more key, which is confirm. I said C lah. Okay, I boleh bercakap confirm lah. Okay. And this is no longer 10 lah. 9, 10 signals is 11. You see, Lokman? So what you are saying can be done. It is up to you as the designer to define this. And what I'm trying to get the message across to you is that it is these little things that is going to make your design like sell 2 times more than other people's design. It is little things like this, whether you have a confirmation key. And now I'm going to show you what is the implication of having confirmation key, no confirmation key, and all these other situations. We're not done yet. There's plenty to unpack from even this simple example. I just want to see from your perspective, how many of the problems can you spot the lack of details can you spot, the lack of specification? Because usually when you have lack of specification, that's what causes a lot of the problem. So you can say you need one more. Here you have a confirmation key. After this, only unlock. And this will be locked. Okay. Now that you have introduced the confirmation key, I'm going to ask you another thing. Here I've only defined a sequence of 4 numbers before the confirmation key. Are you going to accept more than 4 numbers or less than 4 numbers after the confirmation key, before the confirmation key? Yes or no? Is it possible? Can I press 3 numbers then press confirm? Can I press 5 numbers and press confirm?
Yes.
Yes. In that case, this specific, sorry.
Yeah, correct.
Yeah, so in that case, this specification here is no longer complete already. Why? Because I'm only showing you what happens when there are 4 keys. What I need to say is every other sequence with arbitrary number of keys. So I can put something ... lah here, just to say, right? Arbitrary number of keys. That means whether it's 3 states, 2 keys, 3 keys, 4 keys, whatever it is, after you press confirm, it will still be locked. Whereas here, this exact 4, after you press confirm, it will unlock. Then in this case, it is complete, this specification. Okay, so in this case here, I would say this is confirmed. Then in this case, it will remain locked. The confirm key here, this case also will be locked, and the confirm key here, this case also it will remain locked. You see where this is going? Where this is going is I want you to think before you start any design, you need to specify this completely. Once you specify it completely, you understand the design you are trying to do. If you don't specify this completely, you're going to get headache in the middle of the design, and you're going to think the design is difficult. No, the design is not difficult. It's impossible because you've not specified what you want to do, right? So this is the major mistake that most undergraduates who have not had enough of practice with this, you make the mistake here. You don't completely specify how your system should behave. Now, based on this, with the confirm key, is this design complete? Do you think it's complete? Is there anything else that I missed? It's not a design yet, sorry. Is this specification complete? Is there anything else that I missed? Yes? Oh?
Maybe additional output, alarm.
Alarm. Okay. You want to have an alarm. Okay, what does the alarm do?
When you enter password wrong 3 times and then it sounds the alarm.
Okay, can. But I would say the alarm would just be, okay, okay, can. We can add alarm. Anything else?
Or maybe like after a certain number of tries, you cannot, the whole system will lock. So most alarms have that. Like
There
you
we
can try a
go.
certain number of times and then the
There we
system will
go.
reject.
So how many times you want to lock the system before you lock them out? How many
Maybe
times?
a maximum of 5 tries before
Five.
it's completely
5
locked.
tries, system locks. So what does system locks mean? System lock means this is no longer allowed to unlock. Is that correct?
Yeah, correct.
Correct, huh? So then this specification is not complete anymore. You have to say if a number of previous incorrect tries less than 5. Okay, it's like that. Is this complete? Because then what I say, if the array number of keys or number of incorrect tries greater or equals to 5. Okay, so which means that after 5 incorrect tries, you have this will still be locked. It won't be unlocked, correct? Okay, now, is this complete? It's not complete. Why? Because you have not mentioned that after you unlock this, let's say you have 4 incorrect tries, you unlock this, then you have 1 more incorrect try. Is that counted as the 5th incorrect try, or is that counted as the 1st incorrect try? That means now I cannot just consider this sequence. Okay, I have to consider going to do okay, so these are 4 incorrect tries, right? Previously. So I have this try here is correct. Okay, so it unlocks here, right? Then I have 1 more incorrect try here. So what is the behavior after this? What is the behavior of this? Is it lock or unlock?
That means this one is after 4 incorrect tries.
Yes, I have 1, 2, 3, 4 incorrect tries. 1 correct after that, and then 1 incorrect try.
I think like after it gets correct, right, it should reset everything back.
Okay, then you have to state that in the specification because I could actually assume that I have 1, 2, 3, 4, 5 incorrect tries. That means this one has to lock. Or I could say that after the unlock, this is considered 1 incorrect try. You must say that. You must say incorrect tries reset after a correct unlock operation. Now, is this complete?
We can add a bit.
Add what?
Like for instance, the number of tries we do, like for instance, like after 5 times we get stop right. Like
Yeah.
sometimes in our both system, like our phone, for instance, that sometimes when we type the password wrong for a certain number of times, it goes locked and then it says you can only try back after a certain number of times. So we can have this time factor where you have to wait for a certain amount of period of time before the system resets back itself. So you cannot like, try during that period.
Okay, that means is it incorrect tries reset after correct unlock operation or after how many minutes?
Maybe can set as 20 minutes or 30 minutes.
30 minutes. Great. Are we done?
I think so.
Okay, anyone else want to add? Okay, I don't think we are done. We haven't talked about the duration of time between key press. That's number one, very important. Okay, what if I press one key and then I wait 1 hour to press the other key? The second is, are we hard coding the password? It means you build this chip, you only can put 5606 and nothing else. And it's not very useful because everybody who buys this chip will know that it's only 5606. So it's pretty much useless. So we have to have the ability to set the passcode. And then, do you want the ability to set the passcode to arbitrary lengths? Okay, so ladies and gentlemen, my key point here is that you have seen just by one simple example, we can keep growing the design and growing the design and growing the design and growing the design and growing the design until you look at this and you're like, oh, wow, I have specified what it needs to do, but now Dr. Ho had better tell me how to design this darn thing lah. And we will do it. We're going to save this and we're going to do it. Maybe you can do it as a homework and then I can also do one in class and show you how it's done. Okay, but the key point here is you've learned a lot of things already from here. Number one, complete design specification. You need to know what your inputs, what your outputs. You need to know the encoding of your input and the encoding of your output. You need to define the sequence, the operation for a given sequence of inputs. What is the sequence of outputs? So here is it specified? Yes, I specified my inputs are 5, 6, or 6, or whatever else lah. It doesn't say how many number of sequence here, any number after the confirm button. And my outputs, the sequence also mentioned lock, 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 unlock, lock, 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 lock. So the sequence of input outputs. And in that process, you see it starts to get a bit crazy because of the sequence. I have so many possible sequence that I have to consider to ensure I have covered all the use cases. Because if I make a mistake, as I said, or I change the definition, the behavior changes. Remember, we were changing lock, unlock here and all that. Then, the behavior changes based on how you define. And if you don't define, that's the worst situation. You let the synthesis tool kind of make the decision for you and you actually don't really know how your design works and something happens and then it breaks and then you say, oh, I don't know, the tool is problematic, this is some black magic or all that. No, it's because you were not thorough enough. Okay, and I said the key problem here is you need to actually consider all the possible sequences. Okay, this is what we mean by specification. Now this is a short form. Okay, this is also a short form. Okay, I put 55cc5, but actually what you actually need to be able to understand and to do, okay, I'm not saying you have to do all of it, but you must be able to at least show a few representative. You cannot just say 555c, right? You will have a table or you have a diagram where you will actually put, for example, the exact digital bits, okay? The exact digital bits. So like let's say we use this encoding lah. we use this encoding lah, the integer encoding easier a bit. No, this is the integer encoding, sorry, this one. Use this integer encoding here, okay? Or I'll say the one hot encoding lah. We do both lah. What you actually need to do in order that you have this sequence here, okay, we have this sequence here. Okay, let's say the behavior here, right? This is one behavior. I actually must be able to write or draw, we would say key 0, put key 1, let's say key 5, and then key 10. Okay. You must be able to draw the timing diagram. So the first key 0, let's say I'm using one hot encoding lah, because they're 10. Okay, so key 5, logic 1 is press. Okay, key 0, key 10, this is the confirm button. Okay, key 0, key 1, press. Also not press. Okay, so can you see this is 5, 5C? Can you see that? Okay, if you cannot see, ask me. So can you see? Can somebody just confirm? Do you understand the diagrams that I'm drawing?
Yeah.
Yes, sir. Okay. So ultimately, a complete design specification, you must be able to draw this diagram, right? Inputs and outputs, you must be able to draw, and you must be able to label what is this timing. And when you do that, you start to see all the possible problems that can go wrong that you have to specify lah. You think this was completely specified? No, this was with the assumption that you only press one key at a time. Now let's go back. With one hot encoding, is it possible for me to press 0 and 1 at the same time? That means, can I do something like this? Is it possible for me to do this? Can I press the two keys together with one hot encoding? Is it possible? Yes, no?
No, one hot encoding, one event only happen one time, right?
It depends on how you code it, but if I'm just saying that I have a switch and whenever I press the switch, the logic goes 1, they are independent lines, right?
Yeah.
Right? And if you actually look at the keypad, that's what the switch is doing. It's just a little carbon contact, and then once you contact, you get a voltage there already. Right? So Gabriel has a point. His point is basically, if you really define that this is not possible, it's not possible. But you have to ensure from the circuit perspective, it's really not possible. If it's a simple circuit, it's possible. And this is the worst case. You see what I just did here? You press 1, then you press 0 without lifting the 1, and you lift the 1, and you press the key number 5, Then you press you holding down the key number 5, you hold down the key 0. So now at this point, I'm holding down 2 keys. Then I let go key number 5 and I'm still holding down 0. What do you do in this case? Right? So this is just to illustrate to you. Again, you have to define how these cases are handled, right? Because you cannot just blindly assume they are not that way. The signal doesn't work like that, right? Like say if you have a digital circuit, right? You are specifying these are your input pins, right? So when you design maybe the IC for this, right? These are your inputs, right? You can tell the designer, oh, okay, you have to actually align this, you know, you can only press these in a certain amount of time, but what if the circuit that is inputting to your circuit doesn't obey that? Then will it really mess up, screw your circuit up? Right? So you have to consider that, right? And one way people have worked around this is they don't take pure combinational like that. They define a clock signal. Okay, so now I'm going to actually draw a clock signal in a different way because I'm a bit tired of drawing it the whole way. I'm just going to draw up and down arrows so you know that this is the clock edge lah. Okay, you can follow. So you define up and down signals in such a way that you only allow the readout of you only allow yourself to update inputs, okay, on these up and down signals, right? So let's say this is the true key. Okay, this I just call it the true key lah. Real key 0. And then this is my key 0. This is the input signal lah. Okay, so if this is the real key 0 and it's changing like that, then my key 0 actually is going to change only at the edges here. So that means it will change at this. Let's say I put the negative clock edge lah. It will change at this point. Okay. Right, it will change like that. Okay, and the reason I show you this is because you now are introduced to this concept that the clock, the system clock, is actually a synchronization mechanism in all digital circuits. It is to allow you not to go crazy at when the signal changes, when it arrives and all that, because you can easily solve that by putting this real key. You put this real key, you put it into a D flip-flop. Okay, this is a D flip-flop. This is real key 0. This is key 0. This is your clock. And if you do something like this, you actually don't really have to worry about when real key 0 changes, because when you do this, you sort of guarantee the property of key 0 signal. This signal will only change at the positive edge of the clock, for instance, or the negative edge clock, depending whether this is a positive edge or negative edge flip-flop. Okay, so this is a way for you to actually keep yourself sane, that you can only expect the inputs to change on every clock edge. Okay, so this can change whenever, but this will update at the nearest clock edge after these changes. You follow me? Can you follow this?
Yes, Doctor.
Okay, great. Okay, so now let's look at this. We are actually changing on the negative clock edge, so this is great. This is actually changing. This is like 1 clock cycle lah. But what happens if I were to actually stretch this out like that? So you can see this is going over 1, 2, 3 clock cycles. Do you interpret this key held down for 3 clock cycles? Do you interpret this as 1 key press or 3 key presses from 0?
probably 1.
Very good. I think the person who mentioned this is aware that usually the clock is very fast. Simple design like this, you can go for maybe 100 tens of kilohertz to 1 megahertz, but in a processor you're like 1 gigahertz lah. So it's unlikely you can press the key in less than a second lah. Okay, so you probably want to actually have a mechanism where if there is no release, you just consider it's 1 keystroke. That's why I mentioned the timing here, the duration between key press is very important for you to specify. Because if you don't specify a duration, this arrow usually means 1 clock cycle. And this is another very, very, very common mistake from undergraduates, people coming fresh out of undergraduate. Okay. All right, ladies and gentlemen, it's getting kind of late. I'm not sure we have time or you are so inclined to go through the circuits part, but let's actually wrap this up. I give you the overview, the big picture. What have we done tonight? I have emphasized to you that the very first step of design is not design. The very first step of design is you have to completely specify what you are designing. You don't do this, you're going to suffer and it gets worse. Your suffering gets worse, it gets compounded as you progress in the design, because it's not that the design is difficult, it's because it's impossible to design something that's not defined. So you end up defining things on the fly, and in the end, your system doesn't quite work, right? So rather than that, you pay attention, you start by first completely specifying the design. And here I'm actually indicating to you several ways to do it. Okay, several important things. The first step is you always think about your circuit as a black box. There's going to be inputs, there's going to be outputs. You need to specify how many input pins, how many output pins, what are the names of those pins, what do they mean, what is the encoding, okay, what does logic 0 mean, what does logic 1 mean. And then you have to specify the complete sequence, all possible sequence of inputs. You have to completely specify what is the sequence of outputs, right? Because you're not just going to get one input here. The input is going to be changing over time. There is a time property to how it is. And the whole point of your circuit is to respond to this change in inputs over time. So you have to completely specify what is the change in output. Here we've done it in a clever way because we look at the pattern. There's only one pattern and then there's all other patterns. We said no. So we're defining the sequence in terms of pattern. So these are the things that you sort of have to look up for, right? And this is where I can relate back to control and data path. It is impossible for you to define every possible outcome from a data path. Let's say you want to say I want to add 64-bit numbers, two 64-bit numbers. If you want to completely specify all the input combinations, you have 2 to the power of 64 times 2 to the power of 64 possible input combinations on the data path. You don't do that. You say this is the data path. There's any arbitrary number. There are 2 to the power of 64 combinations of number A and number B. What I do is I add them together, and the add operation is like you have a separate table that you can actually show what it is. Okay, right? So that's how we think about data path, because the key idea of data path is there are many kind of different data, and it's not possible for you to list down the truth table, all the possible combinations of the data. You try to find a pattern. But the control path, usually you have to specify in detail, right? Because the control path is the important one. It's like from here, from here, from here, from here, from here, right? So again, here, I'll give you an example. What is the control path? The control path typically is whether you're choosing to lock or unlock, confirm or not confirm, evaluate. Those are the control paths, the circles of the control path. The data path is actually the sequence of pin numbers, passcodes you are receiving, because you will then compare these pin numbers or passcodes to something. All right? Can or not? Make sense?
Yeah.
Okay, so complete design specification. You have to start every design with a complete specification. Draw a black box. Give the complete listing of what are the inputs, how many bit width and all that, what are the outputs. Define, name every single input pin. Define the logic level. What does logic 0 mean? What does logic 1 mean? Because you can see, again, even if you say a numbers, I mean 2 numbers, I have fixed point, I have 2's complement, I have 1's complement, I have floating point, IEEE 754, I got 32-bit floating point, I got 64-bit floating point. There are so many different number representations. Or if you are looking at text, right, you have the ASCII, you have the Unicode. So different bit combinations mean different things. So your job when you specify is you really have to define clearly what is the encoding, what does every bit mean, what does all the patterns mean. You have to define in response to all possible input sequences, what is the output sequence, okay? And then you start looking for all the possible cases where things can fall in between. Like, you know, if I press two or more keys together, what happens? I press one key, then I lift it up, then I'm pressing another key, right? What happens? Or like if I hold down the key for very long, what if I hold down the key for 1 hour? You know? And why do you need to do that? Because that's exactly what hackers do. They try to find out all the slipshot and shortcuts you take in the design, utilize it, and hey presto, they break your system. All right? Okay? So a complete specification lah. Of course, this one you can actually put it in text, but the best case is if you can actually just translate and show timing diagrams like this and explain lah all the possible along with state transition diagrams like that lah. Okay, can or not? I wouldn't actually say the state transition here. This one you just you diagram it like you, as long as it's clear, it's understood that this is a sequence and all that, it's okay. All right, is that clear?
Yes.
Okay. You guys want to go on for another 5 to 10 minutes, or you're very tired already? A bit tired, huh? Okay. Ken, then it's okay because I'll just give you a very brief preview what is next lah, but the key part is next. There are quite a few sequences next. So the first step today we covered, this is how you completely specify a system. Okay, a digital system. You need to think this through carefully. You don't think this through, it's a problematic thing. After you've thought this through, the next step is to specify how you will test this system. You see, we haven't even talked about design yet. Now that you have all these possible things, you tell me, let's say if I have a design here, how are you going to test it? So that's the next step lah. That's step number 2. After you finish these 2 steps, so step 1 is specify what the system will do lah. This is the specification. Then how to specify how you test this system. Okay, that means what sort of input patterns you're going to push it in, and what sort of output patterns you expect. Because if you've done a good job, number 1, number 2 is going to be straightforward. You know all the difficult cases. You have to list them down. And 1 and 2, you haven't started the design yet. You are just saying what is it you're going to design. Okay, all right. Number 3 is where you start the design, and it's a stage where I said you design the hardware model. Number 4, you translate the hardware model into circuit or Verilog. Number 5, you write the test bench. That's your design process. That's it. 5 steps. Okay. What I will sort of do is just the next sessions we will talk a little bit about this, all this in this sequence lah. What is a hardware model? Hardware model, your state transition diagram, that's actually a hardware model because it's telling how you are going to implement this sequence. Right? We've not finished yet, right? This is just one thing, but you know what is the states that you have. So it's going to start introducing you to the concept of states. You didn't know what a state is, but I just want to reinforce because a state is basically a mode in your hardware. Right? It's basically answering the implementation question. You need the hardware to behave in this way. How are you going to get it to behave in this way? You understand what I'm saying? So hardware model is usually state transition diagram or algorithmic state machine. So I think the textbook, the Choose textbook calls it FSM, FSMD, and AFSM, I think, algorithmic FSM. So you can go and look at it lah, right? So FSM is bubbles lah, where you define it in terms of state. Algorithmic FSM is like a flowchart. There's an if and else and all that kind of stuff. And where we're going to go with the translate hardware, you will see I can actually draw circuits. like this. I can say if, for example, if pin code, if sequence equals pin code, then unlock, else lock. 0. Lock is 1, right? So this looks like actually you can implement this pseudocode using a multiplexer. I think some of you have seen it last time already, but this is for the benefit of those who didn't take VLSI. Multiplexer, and then you're specifying this is the output pin unlock. Okay, so there's going to be one condition. Okay, this is just a preview lah. I'm going to talk about this in more detail in the next session, but this is just a preview. So unlock. So in one case, I will unlock it. And in the other case, I will keep it locked. Okay. This is my condition. So what is my condition? Sequence equals pin code lah. Okay, so how do I do this, right? So this is actually a signal that is coming out from a state machine that I look at all this. So when I press the confirm pin, this unlock actually can go in as a control signal here. And this is the data path to unlock it. Can, right? Or another way of implementing is I can feed all of these numbers into a shift register. And then I just compare the shift register to the pin code. There are pros and cons. We will talk about the implementation later on in a future session. I'll save this. I'll put it onto UlearnX. But this is where we're going because we're going to now start to see after we specify how we test the system, how do you actually generate a hardware model. And again, this one, very simple, right? This is actually always. And this is already very long code already. Right, so what I'm trying to say is these specific structures, there is a very specific Verilog code, and you can start to map it, right? And then we'll start to throw in D flip-flops, and then you will just see that state machine is actually very simple. It's not very difficult. It's more important how you define the states, input and output situation and all that. All right, okay. I'm going to end here, and I'm going to ask you what I've done is I have scheduled every Friday of this semester but I recognize you're not going to be so free. You're not going to be attending every Friday because it's quite heavy. So I just put the calendar there so that if we agree that you want class, then we'll have the class. If not, we will cancel it Now my worry is that if we wait until next Friday, it'll be a little bit late for you to actually pick up everything, because these are the basics. This is something that has to be completed in another 2 or 3 weeks, because I'm not actually teaching you anything different or new. You should know all this already from the electronics, but I'm just reinforcing some of the things that maybe you've not have enough practice or you've not actually thought about. Okay, so would you like to have another class like within the week, or you guys are okay to have another next class next week Friday?
Maybe fine, but just let us know in advance.
Sorry, can you repeat that?
For me, any day is fine, as long as we are notified like in advance a bit.
Okay. Okay, all right. So I think it's quite late already, so I won't keep you all. I may try to suggest something before Friday I don't know, Sunday night. Are you all keen? Okay, never mind. I'll just put it in the WhatsApp lah. Then maybe you all take a poll lah and see if you're okay or not. If not, then we will just do it the next Friday if everyone can't make it in between lah. Okay. But in the meantime, I really do hope. Please go to the Chew textbook. Chapter 1, Chapter 3, you need to review that as quick as possible because it's combinational logic. You really should start your studying on chapters 4, 5, 6. It's not very long. Okay, you'll be able to finish it, I would say, in one sitting. One chapter probably in one sitting. Few hours, like maybe half a day, you can finish one chapter if you really go through the code. But it's probably going to be a bit faster. Right, and then Delhi would be sort of complementing if you miss any of the concepts. You really have to pick up the design aspect of things. And your main point is the PBL project, the FPGA. Most likely, I will give you maybe some additional small homework assignment. You'll be something like maybe design a circuit like this, or we will go ask you to design maybe an I2C decoder, looking at something like that. Okay, just to reinforce the concept. Okay. And get you to get some practice. But if you're really getting practice, if you're already doing some of the homework questions in the book, you can actually just put it together and submit it, and maybe I consider that as the assignment already, because I'm not really interested in overstressing you. I just really want you to focus on this project and get a really good understanding and able to design a system that can read and write to SDRAM, and you can implement it on FPGA and you know what's an FPGA. If you achieve that, that's more than happy for this class already. All right. But the other smaller design, just I would say, is just ways to kind of mitigate your risk to give you free marks if you put in the effort, that kind of thing. Yeah. Okay.
Yeah.
Okay. So, ladies and gentlemen, any questions before we end for tonight? Anything you want to ask before we end for tonight?
Doctor, just a quick question, Doctor.
Yes, Lukman.
Say that since we only have this one PBL, right, and it's quite major like you have mentioned.
Yeah.
So meaning that the EA is more or less is like PBL. Just asking.
Okay. Great question, Lukman. The last time I offered this, because this PBL is not the complete SDRAM, I'm just asking you to implement parts of it. So if I just pull up the SDRAM data sheet, this is the circuit, and just to show you, this is all the possible signals. So it's got the time diagram. This is a state transition diagram for this. So the assignment was actually implement maybe something like this and something like this only, but not all the other transitions. You're not implementing all. I think it was just like that. Read, then you go to pre-charge, then you go back to idle. So it's just specific trajectory only in this state transition diagram. So what I did in the last time was I got the PBL, they do one transition, and then in the exam I asked to do another different transition somewhere. So you can reuse most of the circuit. I would either do it that way for your EA, or I will give you a simple problem like something like maybe this kind of passcode design. So you design it from scratch, you implement it, you give the test bench, everything. So it will be either one or the other only. But whether it is implementing one of these or implementing something simpler like this, I don't know yet. I would like to really see your progress in this course. So PBL is the main one, but I may actually ask you to do 1 to 2 more smaller design work for this course just to submit and like I said, if you happen to already doing the textbook and you're already doing a design, let's say you go to chapter 5, you're already doing, let's say this got all of these here. Okay, you pick maybe at the end here, you are already doing maybe not the parking lot counter. There were questions. Maybe you're doing, so maybe you're already implementing the parking lot occupancy counter, right? So maybe I can consider, I will just say if you've done this complete, match the rubric with the specification and everything, I can consider to actually grade this rather than I give you, just tell me you do it like that also can work so In total for this course, I would say the PBL is the main one, the FPGA SD-RAM controller. The EA will either be something similar to the PBL or it will be a simpler design, something like the passcode or I2C or SPI controller or something like that. And then there could probably be, I would say, maybe two more smaller designs, which either you can pick from the textbook or something decently complicated, but not overly complicated. You do a thorough job there, or I will give it to you lah. We will see in the coming weeks lah. But the two smaller assignments is going to be things that help you, not hinder you lah. I'm not sure yet lah. Maybe one of the things I could do would also be, since we're designing the passcode and we are actually going to go through the design and all that, maybe I'll ask you to finish up this one and actually write the Verilog, simulate it, everything lah. I might ask you to do that lah. So that could be one assignment lah. So it will be a bit more straightforward because it's guided. Then maybe there could be a second one lah that we design, we go through. Is that okay, Lukman? Does that answer in total? So I'll say you are looking at most 4 things lah. PBL, FPGA is the main one for SD-RAM. There are probably 2 smaller ones which maybe we'll just integrate in the class, and then that's the EA. Is that okay?
Yeah, understood, Doctor.
Okay.
Yeah,
Great.
thank you.
Great. Yeah. So my goal is not to torture you or anything, but it's you need to learn how to design and really be able to do it lah. If you're not able to do it at the level of the SD-RAM, maybe we can look at it at a simpler level. It's also okay lah. And if you take a look at the SD-RAM, if you feel after even 2-3 weeks is really complicated, talk to me. We can have a dual mode lah. Of course, we like to stress the Intel people, so we will say Intel people will do the SD-RAM stuff lah. But maybe for another track, if you really want, I will give you a simpler assignment. PBL also can lah. So there are certain ways this could be flexible, but let that not stress you too much lah. It's more important you do the learning in lockstep with me lah. Like you really have to get started on the learning and do your practice and all that lah. The key is just do lots of designs. Yeah. Okay. Any final questions? Anyone? Okay,
No.
going once. Sorry, Lukman says no. So going once,
Yeah.
going twice. All right. So wish all of you a good night, and let's touch base again on the WhatsApp to see if I could have another class soon enough, so I can actually move you all faster through the learning process. Okay. All right. Okay.
Thanks, Doctor. Good night.
Okay. Take care,
All right.
everyone.
Thank you very
Thank you,
much,
sir.
Doctor,
Good
and
night.
everyone.
Yeah.
Thank you, Doctor.
Okay.
Bye.
Bye.
Thank you, Doctor.